Welcome to Ask and Learn.
So for the domain, we know that it's going to be x is greater than 0 because it has to be, first of all, x cannot be 0 because of the first part. And the second part tells us that it has to be positive. So x is greater than 0. Intercepts, there are none. Symmetry, there's none. And for asymptotes, if we look for a horizontal asymptote, for example, we have to set limit as x approaches infinity or limit as x approaches negative infinity. We see that there's no horizontal, however, there is a vertical asymptote at x equals 0 because we set our denominator for 1 over x. We set the denominator to 0, so x is 0 is our vertical asymptote. And now we look for increasing, decreasing intervals. So we find the first derivative, y prime, and that is 1 over x minus 1 over x squared. And if we set our first derivative to 0, we can find critical points, and we see that x is 1 is a critical point. So if we do a first derivative test, so this is for f prime, and we substitute, and we search for inside of our derivative, we're going to plug values that are smaller than 1, but we have to remember to stay in our domain. So if it's smaller than 1, it's going to be negative. If it's greater than 1, it's going to be positive. So that means that it's decreasing until it gets to 1 and increasing after that. So if it's going from negative to positive, so decreasing to increasing, it's going to be min, a local minimum value. And if we want to know the y value of our critical point, we go f1. So we're putting it back into our original equation to find 1. So 1, 1 is our minimum, local minimum value for our graph. And now we can find, we can look at concavity for this graph by finding the second derivative. So y double prime equals negative, and this negative is on the outside of the entire fraction. So negative x minus 2 over x cubed. So if we set that equal to 0, we see that x is equal to 2. And now our second derivative test. So f double prime, and this is 2. And we have to make sure to test values in our domain. So for example, if we test 0.5 for over here, so smaller than 2, but still inside of our domain, we're going to get positive, so concave up. And beyond that, it's going to be concave down, so negative. Okay, and now we can graph with the information that we got. So first thing I'm going to put on the graph is the vertical asymptote at x equals 0. And we can see that we have a minimum value at 1, 1. So let's say this is 1, this is 1. So that's our local minimum value. And we see that we have this is an inflection point because it's switching signs from concave up to concave down. So we can say that this is an inflection point at 2. All right, so let's say this is about 2. So this is a rough sketch of our graph. It's going to be decreasing until it hits our minimum value, so it cannot touch the asymptote, so decreasing until it hits the minimum value. Then it's going to increase from then on, so we have concave up, that's correct, and then it's going to be concave down after it gets to our inflection point. So it's concave up, but still increasing until it hits our inflection point, then it's going to be concave down, but still increasing. And that's a rough sketch.